Welcome to the exciting world of advanced machine learning. How do self-driving cars navigate? How Netflix recommends shows? Or how doctors diagnose diseases? It's all powered by machine learning. Computers learn from data, identify patterns, and make predictions. In today's world, machine learning is indispensable. From finance to healthcare, its applications are limitless. As data grows, so does the need for skilled professionals. This is where you come in. Master machine learning to tackle real-world problems and drive innovation. Build models, make predictions, and advance your field. Whether you're a data scientist or a tech enthusiast, this course equips you to excel. Dive into advanced machine learning and unlock endless possibilities. Machine learning goes far beyond the basics. True mastery lies in advanced techniques applied to real-world scenarios. This is where the real magic happens. Imagine predicting customer churn with remarkable accuracy, or detecting fraudulent transactions in real time. These are glimpses into the power of advanced machine learning. Embarking on the journey to mastering advanced machine learning may seem daunting at first, but we're here to assure you that it's an achievable and incredibly rewarding endeavor. This course is carefully structured to provide a clear and concise learning path, breaking down complex concepts into digestible modules and reinforcing your understanding through practical examples and hands-on exercises. We'll start by solidifying your understanding of the complete machine learning workflow, from data collection and pre-processing to model deployment and evaluation. You'll gain a deep appreciation for the interconnectedness of each stage and learn how to navigate the entire pipeline effectively. Next, we'll dive into the art of feature engineering, a crucial aspect of building robust machine learning models. You'll discover how to transform raw data into meaningful features that enhance the predictive power of your models. We'll explore various techniques, including encoding categorical variables, handling missing values, and creating new features through interactions and transformations. Every successful machine learning project begins with data. It's the lifeblood of our models, the raw material from which insights are extracted and predictions are made. Just as a sculptor needs high-quality clay to create a masterpiece, we need reliable and relevant data to train powerful machine learning models. But not all data is created equal. The quality, quantity, and relevance of our data directly impact the performance and accuracy of our models. Imagine trying to predict stock prices using only the daily temperature. The data is readily available, but it's unlikely to yield accurate predictions. That's why the first step in our machine learning workflow is data collection. We need to identify the right sources of data, gather it efficiently, and ensure its accuracy and completeness. This might involve web scraping, accessing APIs, or working with existing databases. Once we have our raw data, we move on to data cleaning, a critical but often overlooked step. Here, we handle missing values, deal with outliers, and address any inconsistencies in the data. This meticulous cleaning process ensures that our models are trained on the highest quality data possible, leading to more reliable and trustworthy results. Section 2. Preparing your data for action. With clean data, we transform it for machine learning models. This step is called feature engineering. Think of it like turning raw ingredients into a meal. We might combine variables or encode categorical data. The goal is to create features that represent data patterns. Section 3. Building and optimizing your model. Now comes the exciting part, building our machine learning model. We have a plethora of models at our disposal. The choice of model depends on our problem, data, and desired outcome. Do we want to predict a continuous value like house prices? Or are we dealing with a classification problem like identifying spam emails? Once we've selected a model, we need to train it using our data. This involves feeding the model with data to learn patterns. But simply training a model isn't enough. We need to ensure it performs well on unseen data. This is where model evaluation and hyperparameter tuning play a crucial role. We use techniques like cross-validation to assess the model's performance. Furthermore, we fine-tune the model's hyperparameters. By adjusting these, we optimize the model's performance. This iterative process ensures a model that generalizes well to new data. Section 4, from prototype to production. Congratulations! We've built a powerful machine learning model that's ready to make accurate predictions. But our journey doesn't end there. To truly harness the power of our model, we need to deploy it into a real-world environment where it can make a tangible impact. This is where model deployment comes in. We need to integrate our model into an existing system or build a new application around it. This might involve creating APIs, building web applications, or deploying our model on edge devices. But before we hit that deploy button, we need to ensure that our model is robust and scalable. We might need to optimize it for speed and efficiency, especially if it's handling large volumes of data in real time. And once deployed, we need to continuously monitor its performance, retraining it periodically with new data to ensure it remains accurate and relevant. This continuous learning and improvement cycle is at the heart of successful machine learning deployments. By embracing this iterative approach, we can ensure that our models continue to deliver value and insights over time, adapting to changing data landscapes and evolving business needs. Welcome to the fascinating world of feature engineering, a crucial stage in the machine learning pipeline. We transform raw data into a format that our models can understand and learn from effectively. It's the art of crafting meaningful features that capture the essence of the data. Imagine predicting house prices using only the number of bedrooms and bathrooms. Feature engineering bridges gaps by creating new features or transforming existing ones. We empower our models to make more accurate predictions and uncover hidden insights. Often, our datasets contain categorical variables like colors or countries. While these are easily understood by humans, machine learning algorithms need numerical input. Categorical encoding converts these variables into numerical representations. Techniques like one-hot encoding and label encoding are commonly used. One-hot encoding creates binary features for each category. Label encoding assigns a unique integer to each category. Choosing the right technique is crucial for model performance. Numerical features represent data in numerical form, like age, income, or temperature. Their scales might differ significantly, posing challenges for some machine learning algorithms. We use feature scaling techniques like standardization and normalization to address this. Standardization centers the data around 0 with unit variance. Normalization scales data to a specific range, typically between 0 and 1. This ensures all features contribute equally to the model, leading to more robust and reliable results. Section 4. Crafting new features, unleashing hidden patterns. Sometimes the most valuable information lies in hidden relationships between features. Feature crafting or feature engineering uncovers these patterns. It's about creating new features from existing ones. For example, predicting customer churn for a telecom company. We can create a feature like average monthly bill. This might reveal insights into customer behavior. Higher average bills might indicate higher churn risk. Interaction terms and mathematical transformations also help. The key is domain knowledge and creativity. By understanding our data, we enhance our model's predictive power. Section 1. The importance of feature selection. Feature selection is crucial in machine learning. It's like choosing the best ingredients for a dish. Too many features can overwhelm our models. Selecting relevant features simplifies and improves model efficiency. It enhances accuracy by reducing noise and focusing on key data. Section 2. Correlation analysis. Unveiling relationships. Imagine predicting weight using height and shoe size. Height is a strong predictor of weight, while shoe size is less relevant. Correlation analysis quantifies these relationships, providing a numerical measure of how strongly two variables are related. In feature selection, we identify features highly correlated with the target variable. These features contribute significantly to the model's predictive power. Section 3. Recursive. Feature elimination, a stepwise approach. Imagine you're choosing the best players for a basketball team. You start with a large pool and eliminate those who perform poorly. RFE works similarly, removing features until optimal performance is reached. It ranks features by importance and removes the least important. This process repeats until the desired number of features remains. Section 4. Tree-based feature importance. Insights from decision trees. Decision trees provide insights into the factors driving predictions. Each node represents a decision based on a feature. and branches represent outcomes. Traversing the tree helps understand specific predictions. Feature importance quantifies each feature's contribution to the model. Features near the root are more influential. Tree-based feature importance is useful for complex data sets. Section 1. Beyond one size fits all. Choosing the right model. In machine learning, no single algorithm reigns supreme for every problem. Just as a carpenter chooses different tools, we must select the right model for the job. The choice depends on our data, the problem, and the desired outcome. Complex models like Random Forest or XGBoost capture nonlinear relationships. By comparing models, we find the best fit for our needs and insights. Section 2. The power of cross-validation. Unlocking reliable performance estimates. Imagine training a machine learning model and achieving 95% accuracy. But how well will it perform on new, unseen data? Cross-validation helps estimate performance by splitting data into multiple folds. This process provides a robust estimate of the model's ability to generalize. It helps detect overfitting and choose models that balance accuracy and generalization. Cross-validation gives us confidence that our model will perform well on new data. Section 3. K-fold cross-validation. Slicing and dicing your data for robust evaluation. K-fold cross-validation balances computational efficiency and robustness. It involves dividing data into K equally sized folds. Imagine slicing a cake into K equal pieces. Each piece is a fold. One fold is the validation set, the rest train the model. Evaluate the model on the validation fold and record metrics. Repeat this process K times, each time with a different fold. Average the scores from each iteration for the final metric. Section 4. Beyond K-fold, variations on a theme. While K-fold cross-validation is effective, variations cater to specific scenarios. Stratified K-fold is useful for imbalanced data sets, maintaining class distribution. For example, in fraud detection, it ensures balanced representation. Another variation is Leave One Out cross-validation, or LOOCV. LOOCV trains on all but one data point, repeated for each point. It's almost unbiased but computationally expensive, best for small data sets. Imagine you're a musician fine-tuning an instrument before a big performance. You meticulously adjust the strings, the tuning pegs, and maybe even the humidity, all in pursuit of the perfect sound. In machine learning, hyperparameter tuning plays a similar role, allowing us to fine-tune our models for optimal performance. Just as a well-tuned instrument produces harmonious melodies, a well-tuned machine learning model delivers accurate predictions and valuable insights. Manually searching for optimal hyperparameters is tedious, like finding a needle in a haystack. Grid Search CV automates this, exploring hyperparameter values to find the best performance. It evaluates each combination in a grid, performing an exhaustive search. It's like having an assistant trying every combination, sparing us manual tuning. The CV in Grid Search CV stands for cross-validation, ensuring robust performance. It returns the best hyperparameters, optimizing the model's performance. Grid Search CV is systematic but computationally expensive for large hyperparameter spaces. Randomized Search CV offers a more efficient alternative by randomly sampling hyperparameter combinations. This method explores a wider range of values without exhaustive computation. While it may not find the absolute best set, it often discovers near-optimal solutions quickly. Bayesian optimization leverages previous evaluations to guide the search for optimal hyperparameters. It builds a probabilistic model, focusing on promising regions and avoiding unnecessary evaluations. This method often finds optimal solutions with fewer evaluations, making it ideal for complex models. Both methods provide valuable tools for efficient hyperparameter tuning. In reality, data sets are often imbalanced, like in credit card fraud detection or medical diagnosis. Models can become biased towards the majority class, missing the minority class. For example, a model might classify all transactions as legitimate, ignoring fraud. This high accuracy is misleading and defeats the purpose of fraud detection. The challenge is ensuring models pay adequate attention to the minority class. Addressing imbalance is crucial for accurate and effective real-world applications. Techniques like resampling and synthetic data generation can help balance datasets. Properly balanced datasets lead to more reliable and unbiased models. Oversampling techniques increase minority class representation to balance datasets. SMOTE generates synthetic examples by interpolating between existing data points. This method creates new, plausible examples capturing minority class characteristics. By introducing synthetic examples, SMOTE prevents model bias towards the majority class. This leads to improved performance, especially in terms of recall for the minority class. Balancing datasets with synthetic data helps models learn robust representations. Undersampling reduces the majority class to balance datasets. Random undersampling removes majority class examples but risks losing valuable information. Near-miss selectively removes examples close to the minority class, preserving decision boundaries. The choice between oversampling and undersampling depends on dataset characteristics. Oversampling is preferred for small datasets, while undersampling is efficient for large datasets. Combining both techniques often yields the best balance and model performance. Properly balanced datasets improve model accuracy and generalization. Effective balancing techniques are crucial for handling imbalanced datasets. Ensemble learning combines multiple models to create a robust predictive system. Like a team of doctors, each model brings unique strengths and perspectives. This approach reduces variance, improves generalization, and enhances robustness. Ensemble methods combine predictions from different models, reducing bias and errors. This creates a resilient system less affected by outliers or noise. Ensemble learning leverages diverse models for better performance on complex tasks. Combining models creates a powerful and adaptable predictive system. Ensemble learning is essential for tackling challenging machine learning problems. Bagging, or bootstrap aggregating, leverages the wisdom of the crowd. It trains multiple instances of the same model on different bootstrap samples. Each model learns from a slightly different perspective, capturing various data aspects. Aggregating predictions reduces variance and improves generalization. Random forest extends bagging by randomly selecting features for each tree. This further decorrelates trees, enhancing performance. Bagging creates a robust ensemble model by combining diverse predictions. This method is effective for reducing variance and improving accuracy. Boosting algorithms sequentially train models, each learning from predecessors' mistakes. This process improves overall understanding, like a dedicated study group. Boosting starts with equal weights, adjusting them based on model performance. Misclassified examples receive higher weights, focusing subsequent models on errors. Final predictions combine all models' outputs, weighted by accuracy. Popular boosting algorithms include AdaBoost, Gradient Boosting, and XGBoost. These algorithms achieve state-of-the-art results on various tasks. Boosting leverages individual strengths for a powerful ensemble. Deep learning, a subfield of machine learning, mimics the human brain's complexities. Artificial neural networks process information, identify patterns, and make decisions. Deep learning algorithms learn complex data representations, excelling in tasks like image recognition and natural language processing. This ability to learn from raw data sets deep learning apart. It's the driving force behind innovations like self-driving cars and virtual assistants. Deep learning's automatic feature learning enables it to tackle complex problems. Neurons, the building blocks of neural networks, process and transmit information. Each neuron receives input signals, weighted by connection strength. These weights adjust input signals' importance. Neurons sum weighted inputs, add a bias term, and pass the result through an activation function. Activation functions introduce non-linearity, crucial for learning complex relationships. Neurons are organized into layers, each performing different abstraction levels. The input layer receives raw data, hidden layers learn complex representations, and the output layer produces predictions. This structure enables neural networks to tackle diverse tasks effectively. Activation functions act like dimmer switches, allowing nuanced data representations. They determine neuron output based on combined input signals. Activation functions introduce nonlinearity, crucial for complex tasks. Common functions include sigmoid, ReLU, and tan, each with unique properties. Sigmoid squashes output to a range between 0 and 1, useful for binary classification. ReLU introduces sparsity by setting negative values to 0, improving training convergence. Tan centers output around 0, mitigating the vanishing gradient problem. Choosing the right activation function depends on data and task characteristics. Preserving your hard work, saving trained models. Congratulations! You've trained a machine learning model and achieved impressive performance. Now, you need a way to save your trained model. Without saving, you'd retrain your model from scratch every time. Python libraries like scikit-learn, TensorFlow, and PyTorch offer tools to serialize models. Saving a model is like packing a suitcase, making it ready for future use. From development to deployment, bridging the gap. In machine learning, moving from a local model to a production system can feel like crossing a chasm. Development environments differ from production, where models handle real-world data and high volumes. Imagine a self-driving car prototype in a controlled test environment. Deploying it on real roads with unpredictable conditions is a new challenge. Deploying a model requires planning, robust infrastructure, and understanding the target environment. Deploying models as web services through APIs allows seamless interaction. This offers platform independence, scalability, and ease of integration. Building interactive ML applications. Imagine predicting the stock market or diagnosing diseases with machine learning. The true value lies in making these models accessible, allowing others to benefit from their power. Interactive applications share our creations with the world, empowering users to explore and gain insights. From simple web forms to sophisticated dashboards, these tools make data exploration interactive. Python libraries like Flask and Django help build web applications, while Streamlit and Gradio create interactive dashboards. These frameworks simplify user interfaces, abstracting model complexities. Users focus on insights and predictions. Interactive visualizations like charts and graphs help understand complex data patterns. Building interactive ML applications enhances model impact, fostering deeper understanding of data insights. From theory to practice, real-world project ideas. Congratulations! You've mastered advanced machine learning techniques. Now, build projects to showcase your skills to employers or clients. A strong portfolio demonstrates your ability to solve practical problems. Here are a few project ideas to get you started. Predicting loan default. Assess credit risk using machine learning. Classifying customer reviews. Use sentiment analysis to understand customer feedback. Medical diagnosis using images. Assist doctors with AI in diagnosing diseases. Building your portfolio, showcasing your skills to the world. A well-crafted portfolio is your digital resume, showcasing your skills and passion. Demonstrate your ability to apply knowledge to real-world problems. Think of your portfolio as a curated gallery of your finest creations. Each project should tell a story, highlighting your skills and creativity. Section 3. Navigating the job market. Tips for aspiring ML engineers. The field of machine learning is booming, with companies across industries actively seeking talented individuals who can harness the power of data to drive innovation and solve complex problems. As an aspiring ML engineer, navigating the job market can seem daunting. but with the right preparation and a strategic approach, you can increase your chances of landing your dream job. Here are some tips to help you stand out from the crowd and make a lasting impression on potential employers. Attend industry events, conferences, and meetups to connect with fellow ML enthusiasts and professionals. Networking can open doors to unexpected opportunities and provide valuable insights into different companies and roles. Craft a compelling resume that highlights your relevant skills, experience, and projects. Tailor your resume to each job description, emphasizing the specific qualifications and experiences that align with the role's requirements. Technical interviews for ML roles often involve coding challenges, theoretical questions, and behavioral questions. Practice your coding skills on platforms like LeetCode or HackerRank. Review fundamental ML concepts and prepare concise and insightful answers to common behavioral questions. Section 4. Lifelong Learning and Beyond. As you embark on your journey as a machine learning practitioner, remember that learning never truly ends. The field is constantly evolving, with new algorithms, techniques, and applications emerging at a rapid pace. Embrace a mindset of lifelong learning, continuously seeking out new knowledge, experimenting with new tools, and staying abreast of the latest advancements. Here are a few ways to foster a lifelong learning mindset in the ever-evolving world of machine learning. Platforms like Coursera, edX, Udacity, and Fast.ai offer a wealth of online courses and resources, covering everything from the fundamentals of machine learning to specialized topics like deep learning, natural language processing, and reinforcement learning. Stay informed about the latest advancements in the field by reading research papers and publications from conferences like NeuraPS, ICML, and ICLR. While research papers can be dense and technical, they provide valuable insights into cutting-edge research and emerging trends. Contributing to open-source projects is a great way to deepen your understanding of machine learning, collaborate with other developers, and give back to the community. Platforms like GitHub host a vast number of open-source machine learning projects, offering opportunities to contribute to code bases, documentation, or even propose new features. Section 1. Your advanced machine learning journey awaits. As we reach the end of this exhilarating exploration into the world of advanced machine learning, you stand at the cusp of incredible possibilities. The knowledge and skills you've gained throughout this journey empower you to tackle complex, real-world problems, drive innovation, and shape the future with the transformative power of AI. Remember, the path to mastery is a marathon, not a sprint. Embrace a mindset of continuous learning, always seeking out new knowledge, experimenting with novel techniques, and pushing the boundaries of what's possible with machine learning. The field is constantly evolving, and your ability to adapt, grow, and innovate will determine your success in this exciting domain. Don't be afraid to get your hands dirty, to dive into real-world projects, and to learn from your mistakes. The most valuable lessons often come from the challenges you overcome and the insights you gain from hands-on experience. Embrace the iterative nature of machine learning, constantly refining your models, experimenting with new approaches, and seeking feedback from others. Empowering the future with AI. Machine learning is no longer confined to science fiction. It's transforming industries and shaping our lives. Join a community of innovators harnessing AI for positive impact. Use your knowledge ethically and responsibly. Never stop learning and sharing your knowledge.